stuff has been actually quite a bit more advanced than I would rule out, especially any code like this. Okay, so what have we gone over? Let's talk about it based on the schedule. Well, the first things that we saw were a glimpse of how any logic can be used to depict a theory of the world. And in terms of describing that theory, in that case it was a model of natural history of infection where a person was embedded in an environment and interacted with neighbors in a structured way in that environment. We saw how a simulation could be used to play out over time the logical consequences of that theory in terms of the number of people infected, for example, or the spatial character of that infection. And we saw that by modifying parameter values, without doing any real programming to speak of, we could explore different scenarios within the model to examine how does the model behave with different assumptions. And we did that through experiments. And we saw how AnyLogic provides a way of parsing out the logic of a model into pieces. Pieces associated with persons and pieces associated with the global environment. And each of those lives in a different place in AnyLogic. And then there's a place associated with experiments, these sort of scenarios that get run within the model. Okay, want to make sure this is being recorded here. Yeah. Okay, so that was that first model, and it had some implications that went beyond that when we changed the structure of the model. You know, so much of my work is spent in trying to build cross-disciplinary teams for modeling. And, you know, a key part of that is certainly the modeler, the key modeler who builds the model from scratch. And many of my boot camps have been focused to inform those modelers. But many are now focused on building teams that work together effectively to deliver on that modeling, to make useful models that actually get used in practice. And there's many people who might not think about building a model, certainly from scratch, might not even think about modifying a model in some cases, but might think about running a model. So that ability to run scenarios easily is important. And that ability to look at a model visually and parse out some of the major assumptions, maybe not all, but some of the major ones, by visually looking at state charts, for example, is very important to communicate understanding across the team, who may consist of many people with no modeling background, to communicate what's in that model. What does it include? What does it not include? What sort of assumptions does it make about natural history of infection or about the way in which infection is transmitted? So we saw AnyLogic has a very visual way of depicting it, which is very effective for communication. We saw more than that. Lots of things are happening. We saw more than that within our application, within our models, we have the ability to modify things. And we saw that a very small modification conceptually, adding that transition, do you remember that transition from this morning, where people went back from a state where they were immune, that is recovered, to the susceptible state, could have a huge impact on the phenomenology of the model, could change totally what was going on. And either Kim or Amy had mentioned, for example, the idea ahead of time that it would lead to waves of infection. That's exactly right. But we saw what it led to actually differed a little bit by the parameter values. For certain parameters, it led to very pronounced different generations of infections successively. Other parameter values that led to the entire population becoming susceptible again and staying susceptible, and yet others that led to this kind of miasma of people getting infected and recovering more or less in the same area. So we saw that the infection assumptions, the assumptions about that model could really shape in a material way some of what happens phenomenologically in the model. We then went on, ladies and gentlemen, to talk about some of the elements of the AnyLogic vocabulary. We talked about elements involving stock and flow models, compartmental models, which are comparatively small in number, stocks and flows, and you mix them and match them in different ways to achieve very interesting things. By contrast, in agent-based modeling, we have many components we have to bring to the table, many different building blocks. And if you go look at your palette here, it's a testament to that. And many of these we put into place today. Everything from events to parameters to variables to function or to custom distributions. We put a lot of these in effect today. And in general, it's a bigger set of building blocks, not to mention those in the state chart area. In the first little examples, we were using parameters in capturing heterogeneity in a population. This is notable, ladies and gentlemen, because heterogeneity in a population can be hard to capture effectively in large, even very stratified aggregate models. There's a limit of how many dimensions of stratification we can do before the model just blows up in our faces. And it becomes more and more awkward with aggregate models to stratify by additional layers of heterogeneity. More than that, it becomes very cumbersome to experiment with adding a level of heterogeneity because it affects things across more or less the entire model. But in contrast with an agent-based model, adding in a new assumption about heterogeneity, say with respect to a person, doesn't require a lot of work. It's a very localized operation. For example, here, if we wanted to distinguish people by sex, or by age, or by income, we could simply drag in parameters, have a sex parameter, distinguishes people into two sexes. We don't have to go to every state and stratify it by sex. Rather, it's a simple operation. We say a person now has this additional characteristic. More than that, we could capture continuous quantities, things like age, things like income, things like birth weight, that are not really feasible to capture as continuous quantities in an aggregate model. So we saw we could capture heterogeneity, but more than that, we saw that within these models, we could lay out the model and visualize it in a way that speaks to its richness. And we can do so fairly declaratively by setting the properties of people's appearances in a declarative fashion without really writing code. We could actually have them, their size be dependent on income, or their location be dependent on their age, or their color be dependent on their sex. And that's very powerful because it allows us to very quickly sort of set up a compelling visualization for what is often a very complex underlying reality. And it's through visualization we often get the biggest chance of seeing what's going on there. But then it was in the afternoon, really, that things came to the fore in terms of the dynamics of these dynamic models. It was there that we turned our attention to state charts. We turned our attention to state charts as ways of capturing the state of an individual and encoding the rules by which that state evolves, the actions that change the state. And we saw that state charts fulfill both criteria. They specify the states, and they specify the rules that change those states over time for a given individual. A given state chart represents the states and rules for changing those states associated with a certain set of concerns. And in general, we'll have multiple state charts for different sets of concerns. They're not tangled together in a way like they would be within an aggregate model. Rather, they are fairly independent of each other, although there may be interactions back and forth at very localized places. Within a state chart, we have transitions to transition between the states, and those transitions describe how the states can change over time. Subject to being in a certain state, the out transitions from that state say there are these rules for bringing you from that state to another state. And we saw within any logic there's a bunch of types of transitions. And we saw three major types of transitions today. First transition we saw, in the very earliest example, was a rate transition. And that represents a hazard rate, a certain chance per unit time of transitioning from the state you're in to another state. And we mostly talked about fixed hazard rates. They can change over time. And we'll probably see that in the course of this boot camp at some point. But we talked about a hazard rate, and the idea is that that hazard rate, no matter how long you've been in that state, if that hazard rate is a fixed rate, you're going to have the same chance, the same kick of the can per unit time of leaving, no matter how long you've been there. Okay? But beyond rate transitions, we have time up transitions, which specified you leave after exactly an amount of time. And we have message transitions, which specify when you receive a message, do something. So we had a message transition, for example, associated with exposure. If I get exposed to pathogen, then I'm going to flip a coin as to whether I get infected or whether I stay susceptible. Okay, so we saw 3 types of transitions associated with these sort of state charts. And those transitions are some of the most common transitions around. We will see one more as a notable one in the next few days, and that's the arrival transition, which is another common one, particularly for movement of agents, mobile agents. Okay, we may see others at a short level, in a brief way. Okay, so ladies and gentlemen, here within these state charts, we also saw that they could be put to combine with elements of inter-agent communication through the use of messages. And to examine that, we put people into environments which characterized their location, and I would just remember where this is, characterize their location here. You remember here we characterized a person's location. In this case, we distributed them in space according to some distributions, but in general, we could read their location from a database. If they're a farm or they're a city, we could locate it in some GIS space, etc. So we put them in space, but more than that, ladies and gentlemen, we situated them in an environment, and we went up to Maine and situated this population within it in an environment where they had a network which was distance-based, and they were connected with neighbors who lay within 25 distance units of each other, according to a distance metric that can be specified for your model. Having done that, then those individuals who are connected to each other via networks could communicate. In this case, we only used one network, but in general, they could have multiple types of networks in these connections, and they could communicate over those connections. And in this case, that communication led to exposure to messages, and those messages were sent when an individual was in contact with another person or at the starting point of a simulation. We saw in this final session how we could characterize vaccination interventions using an additional type of message, and how we could go implement a vaccination program's implementation in the model by having a sort of number of vaccinations that occur over per day, and at each vaccination occurrence, we look for a person who's eligible and we vaccinate them. This got more complicated than I anticipated when I first proposed it, but fundamentally we could deliver vaccinations to people who met certain criteria, and those criteria could vary on an experiment that is a scenario by scenario basis as to who we wish to vaccinate for our vaccinations, which is a very powerful thing. Rather than changing the model for each alternative policy, vaccination policy or vaccination regime, we can simply encode that vaccination regime within experiments and run those experiments with the model without having to change the model back and forth to accord with different vaccination regimes. Those vaccination regimes are defined by experiments rather than by the model itself. That wrapped it up. So in general, a whirlwind tour of many of the significant features of AnyLogic's modeling. I have to compliment you for your bearing with this. We covered a lot of material, some of which was rather advanced today, and I appreciate your patience and bearing with us, especially without the lack of a TA. Tomorrow we will have a TA, and we'll be going on to additional topics. We'll be taking a look at some ways in which we can extend this model in a couple of ways, and soon enough we will look to combine it with elements of discrete event modeling to take a look at treatment pathways, for example, for individuals or for animals for that matter, which might mediate the recovery, say, from an infection. So we'll be looking at how it links in with some of the workflow side that might be resource limited and limited by the imbalance between need for treatment and resources available to deliver it. We will also be going on to look at some aspects of spatial movement and some aspects of additional sorts of hybrid models in the coming days in GIS. We're going to have a full day of GIS likely on Wednesday, where we deal with the GIS components of any logic. So that's my summary for today. If there's any questions, I'm glad to answer them. As always, I'll upload this model and the videos. I think we lost one of them, but I'll upload the videos, and we'll try to make them available for you tonight if you want to refer to them. Okay? So any questions I can answer before you leave here? Yes?
I guess it's more logistics. So for the individual projects,
yes,
will we have like a set time to work with?
Yeah, so Kurt, I'm going to try to see if I can work with him to set aside some time so that he can pair up with individuals through some of the day tomorrow and in subsequent days to work on these, and then some time for myself to also to come in for certain amounts of time at times that otherwise we'll try to have people work on some exercises, okay? And we'll try to use that to discuss some of the projects, either project ideas, which were identified by participant feedback as being something that people would like to be able to discuss with me or with the TA, and also to be able to work on projects that are already underway to solve technical problems. For example, Irene, I think you have some issues, some needs there that you'd like to pursue, and I think there was some discussion as well about GIS issues with bird migration and bird paths that also needs fixing. And if any of you also have other problems you'd like to ask, how would this be represented in an environment like this? Or you'd like to show models you're struggling with and you'd like some help on them, both the TA and myself will try to have some time set aside for this. Okay, and that will start tomorrow. Okay, other questions? Comments? Okay, full day. Full day. As I say, I am amazed that you were able to accommodate all this. Okay, so tomorrow morning, 8:30 again, I think, Sean?
Yep.
Yeah.
8:30 in this room.
Okay, in this room, and we'll be here, as I understand it, throughout the balance of the week, except for one session on Friday.
Yeah, Friday morning will be in the same room we were this morning.
Great, great. So thanks very much, and I'll upload this last model to the repository as well.
Thank you.
Oh, yeah. If people have projects you'd like to discuss with Kurt and I'd ask that you send me mail if possible. I think you should be able to have access to my mail easily. I think that Sean forwarded an email from me to the group, if memory serves me. So if you could send me mail giving a brief description of the type of topic you'd like to discuss and whether it's for a model already in progress or thinking about what a model might look like, that would help Kurt and me divide up how we're going to handle these requests, okay? And figure out how much time to allocate for different needs.
And the But we were talking, we were back about the tuberculosis.
Yes.